others lead to catastrophic failure, as you can see in this image here. So we work with stainless steels, which are designed to resist general corrosion. However, they're still susceptible to localized corrosion, such as crevice or pitting corrosion. And crevice corrosion occurs when the metal is in contact with another material. So as you can see here, the stainless steel screw has been completely destroyed by crevice corrosion. And on the right is one of our samples, a stainless steel disc, and here you can see the polished surface where at the top and the bottom, crevice corrosion has occurred between the insulator that we coat the surroundings with and the surface. Our main focus of our research was pitting corrosion. Pitting corrosion is when the surface of the metal is penetrated by localized corrosion. And as you can see here, this little tiny arrow shows what you would be seeing from the surface. So it doesn't appear to have affected the metal much at all. However, cross-section shows how deep the pitting corrosion has affected the surface and how much deeper the metal is, and can also be pretty harmful to the metals. On the right here we have samples. This is one of our stainless steel wires, and this is the cross-section of the front. This is our polished surface. And as you can see here, there's many individual rectangular-sized pits. However, after we sonicated it, so using any free or unstable pit covers, we can see how deep the pits have actually been formed on the surface. So our goals for this research was to make stainless steel less corrosive in biological conditions for medical applications such as cardiovascular stents or other applications. And we've done this by submerging our samples in nanopure water at 90 degrees Celsius. And this changes the composition of the surface enough to prevent the onset of pitting corrosion at low potentials. So we've seen these changes in composition on the surface using scanning electron microscopy and energy dispersive X-ray spectroscopy scans before and after our water treatment. So to see, we apply potentials to our surfaces while they're in sodium chloride solutions, and we use 3 optical techniques simultaneously to view what is actually happening on the surface as we apply potential. We try different techniques during our water treatment to find optimal parameters. So here's the setup of our experiment. As I mentioned, these 3 optical techniques. In the center here in the blue, we have our cuvette with our sodium chloride solution, and we have our polished sample in the center. Our first optical technique is elliptical microscopy for surface imaging. We use a helium neon laser, which gets reflected off the surface and is viewed by a CCD camera on the left. Our second technique is contrast-enhanced optical microscopy, for which we use a green LED light and another CCD camera directly in front of the cuvette to view the image. And our third technique is digital anemolography, and we use a solid-state laser. It goes through a pinhole to create a point source of light. This is inside the now, so our camera will be directly in the center and shines perpendicularly past the wire face. So then our CMOS camera directly above is our hologens. So here is our setup again. We have our cuvette and our sample in the center. We have our green LED for treatment, we bend and put our wires to insulate the rest of the wires besides the polished surface to prevent any corrosion happening anywhere else where we can't monitor it using our 3 optical techniques. Then we prepare our cell and our solution, 29% by mass sodium chloride for biological application. And we attach a lid. As you can see on the bottom here, this prevents distortions, which is very important for holography. The camera sits directly on top. And then we align our 3 optical techniques. We apply potential to the working electrode, and then we wait until it hits, and then we process and analyze our data. So here's some of our results, just a general view. We have our potential that we apply as well as the current when an event is happening. We have our microscope image, which shows any changes on the surface. We have our empty image, which is a microscopy for surface imaging, and this shows any changes in the oxide layer directly at the surface. And our holography image, this is our wire here, and this is the solution, and it shows any changes in the index of refraction right at the surface of our polished sample. And with holography, we're also able to track particles that are ejected from the wire face, and we're able to track them through the solution and see how they flow. So here's just zoomed in a little bit more. This is a fairly small event of 0.3 microamps in size. And I just wanted to show here how sensitive our equipment is, because you are able to see it in all 3 optical techniques, which is good. Okay, so here's an example of our worst case scenario for a treated wire and the best case scenario for our untreated wire. The treated wire was 1 hour treated. As you can see, for our untreated wire, the first event occurs at 350 millivolts. This is in potential versus time scale, which are our step formations. And we have a current and log scale versus time, which are our spikes, and these are all events happening. So first event for the untreated wire occurred at 350 millivolts. And then continued pitting, reaching greater than 10 microamps in size by 600 millivolts, by which point the surface has been completely destroyed by pitting corrosion. You can also see in light orange our treated wire started pitting around 450 millivolts, and there was only a few very small events, and then nothing occurred until 800 millivolts, at which point non-load pitting occurred. So here's a bunch more of our data. These only include our 1, 2, and 3 hour treated wires. Our 6 hour treated discs haven't been included yet. All the treated samples are at the top, and the bottom ones are all untreated. They have the same scale of potential versus current. And you can see for the treated samples, overall, there's a lot less events, and a lot of them don't occur until much higher potential. So you see, on average, they usually don't start hitting between 450 to 700 millivolts, while some didn't even start until 1 volt or higher, as you can see with this dark blue or the gray sample. While the untreated samples, they all started between 300 and 400 millivolts, and by 600, the surfaces have been completely destroyed, and no further data is really, there's no point collecting further. I'd also like to mention our stainless steel discs. They have shown very similar results. However, due to the larger surface area, they're a couple of millimeters in size as opposed to our wires, which are only 380 micrometers in size. They have shown very similar results. However, due to the larger surface area, there have been a couple of inconsistencies, and so we're just following up on those. So here, a scan or scanning electron microscopy before and after, as well as our energy dispersed X-ray spectroscopy scan. And we see that there are manganese sulfide inclusions on our surface. Manganese sulfide inclusions are known to initiate pitting sites, and so with the water removal or with water treatment, some of the sulfide has been removed from the surface. So these initiating pitting sites are no longer there to create pitting at low potentials that we apply. So I'd just like to conclude by saying that this water treatment in nanopure water has improved the corrosion resistance of our stainless steel samples in sodium chloride solution. We've seen overall that the treated samples have shown a lot less pitting events, as well as they don't pit until much higher potentials, and they showed great improvements compared to our untreated samples.
So, in the application medical devices, are traditional corrosion prevention systems applicable, like a sacrificial anode?
We don't, like, we know that stainless steel 316 is used for medical purposes, but we don't work with any medical groups or anything like that, so I don't know much more than they are used for medical purposes. I'm sorry.
Based on the experience you're getting in the project, what would you say that are the most important technical limitations in order to apply the system for large scale commercial applications?
Yeah, so our water treatment so far it seems to have just been, okay, so the merge of the samples in pure water, it seems to be just a layer. So there's been some limitations too, because we don't know how sensitive this layer is. If it could just be removed if we wipe it, or so we've been very careful to just scan these samples and test them without having touched them anywhere else. So some of our samples we apply an insulator around the outside of our sample besides the polish surface. And if we do get insulator on the surface, then we can't really wipe them off again because we don't know how that affects the surface. So we're not entirely sure that we're still in the beginning stages of trying to figure out how sensitive this treatment is.
You have to do any kind of a special pre-treatment to your samples before you apply your coating technique?
I'm sorry?
It is necessary to do any special pre-treatment to the samples, any special